Now we come to the chapter of electric circuits, the applications of second order differential equations. And we're going to learn the RLC circuits. Okay, so what is the RLC circuits? RLC circuit is an electric circuits consists of an inductance, a resistor, and a capacitor. And according to Kirchhoff law, it says that the sum of voltages that drop across the inductor, resistor, and capacitor will be equal to the supply voltages. Okay? So, but we know that the VL here is actually equals to the L di dt, and the VR here is actually equals to the RI, and VC is actually equal to 1 over CQ, and then we're going to have another equations in here. Okay. So, but if you look at these equations, this equation does not look like second order differential equations, but we know that the I here is actually equals to dq dt. Okay, what happens if we change the I here into the dq dt? Okay, if we change the I here into dq dt, what happens is I'm going to change this one into dq dt. So we have L d dt with dq dt plus with R multiply with the I. The I we're going to have to change to the dq dt also. And then we're going to copy back this one over CQ and equals to E. Then we have another equations. If we look at the first term here, so the first term here is actually a second order derivative. Okay, so you can rewrite it. So then we have this one. So, and this is actually your second order differential equation for the RLC circuits. Now let's just extract the information from this example. So first of all, it says that you have the ET equal to 150 watts. And you have a resistor of 10 ohms. Okay, so at resistor, we're going to use the symbol R. So we're going to have here, this is actually R equals to 10 ohm. And you have an inductance of 1 Henry. Inductor, we're going to use the L. So L equal to 1 Henry. And the capacitance of 1 over 1900 is actually C. And it says here if the initial current, so current, we're going to use the symbol I. Initial means that at the time equal to 0. And initial charge, we're going to use the symbol Q. Initial means that at the time equal to 0. On the capacitor are both 0. So means that both of them are equal to 0. So then you're going to have I0 equal to 0. And you have Q0 equal to 0. And let's just look at the questions of this example. So the question of this example is they ask us to find the charge on the capacitor at any time t. So charge we're going to say that you're going to find the QT. So this is your questions. Okay, once you have obtained all the information that we need from this example, let's just begin to solve it. Let us solve this example by using its differential equations. So let's just substitute the value of L, that is 1 Henry, and our value of R, that is 10 ohm, and the value of C is 1 over 1900, and the E here, that is 150, and then simplify the third term that you can see here, and this is the second order differential equation for this RLC circuits, and this is actually a non-homogeneous equations. Once we have used the informations of E, R, L, and C, we don't need them anymore, but we still need to keep the initial conditions that are I0 and Q0. Let's just recall what we have learned in the subtopic of non-homogeneous equations. So in the topic of non-homogeneous equations, what you have to do is you have to convert the non-homogeneous equations into the homogeneous equations. Okay, means that you have to let this equation equal to 0. So we're going to apply the same concept in here. So just let this differential equation equal to 0. Okay, so you can convert the non-homogeneous into homogeneous. Okay, once you have converted this non-homogeneous into homogeneous by letting the differential equation equal to 0, the next thing that you have to do is you have to solve this homogeneous equation just that you can get the YC. But in this case, okay, obviously we do not have the variable Y here, okay, but what we have is originally you have the variable Y, okay, but it's actually took over by the variable Q. So instead of you getting the solution YC, you're going to get the solution QC. And then the next thing that you have to do is you have to identify what is your function fx. Okay. In our case, okay, obviously we do not have the variable x here, but what we have here is we have the variable t. So the variable x is took over by the variable t. So instead of finding the variable fx, you're going to find the variable ft. And from the function f, okay, what you have to do is you have to identify your trial solution yp. Of course, in our case, you do not have the variable y. What you have here is variable q. So you're going to identify your trial solution qp. And then you're going to have your general solutions, that is y equal to yc plus yp. So you need to modify this one just so you can use it. So in our case, it's supposed to be q equal to qc plus qp. So once you have understand all the concept on how to solve the non-homogeneous equations in the RLC circuit, let us begin to solve it. Let's solve this homogeneous equation. So what you have to do is you have to change the derivative into m. So we're going to change this one into m squared, and this is going to be m power 1. And this is not derivative, then it's not supposed to have the m. And look at this equation. So this equation cannot have the real roots. Okay, so what you have to do is you have to solve the equations by using the quadratic formula. So which means that your a is actually equal to 1. B is 10, C is 1900. Okay, we're going to substitute the value of A, B, C into the quadratic formula. And then this is what we have. Okay, and then let's just simplify the things that inside the set. So if you simplify, you will have negative 7,500. And this negative 7,500, you can split into 100 multiplied with 25 multiplied with 3 multiplied with negative 1. And set 100 will give you 10, set 25 will give you 5, set 3 will give you still set 3. Okay, this one you cannot simplify. But for set negative 1 will give you I. Okay, 10 multiplied with 5 will give you 50. And let's just simplify it, we have your value m. Okay, and this means that your alpha is negative 5. Your beta is 25 sub 3. Okay, if you have complex conjugate roots, which means that your QC is supposed to be in this form. So let's just substitute our alpha and beta into here. So our alpha is negative 5. Okay, and your beta is 25 sub 3. So we have this one. Okay, so the next thing that you have to do is you need to look at what we have for the FT. So the FT is 150. So 150 is a constant. So if you have a constant, so it means that your QP is supposed to be a constant also. We let QP equal to constant C. So let's just differentiate this QP. So you will have a 0. You differentiate constant, you will have a 0. Differentiate one more time, you will have a 0. So okay, so now let's just substitute all those things that we have here into this non-homogeneous equation. And let's just name this non-homogeneous equation as equation number 1. And let's just do the substitution. Okay, so now let's just substitute our QP double prime into here. We have here that is 0 plus with 10 multiply with, okay, this is actually your QP prime, that is 0. So you have 10 multiplied with 0 plus with 1900 multiplied with Q. So which means that multiply with the C and equals to 150. And if you simplify, that means that your C actually equal to 3 over 38. Okay, so once you know your value of C, okay, that is 3 over 38, substitute into your QP. So your QP is 3 over 38. Okay, now the next step that we're going to do is we need to write our general solution. So your general solution is Q equal to QC plus QP. So which means that Q is equal to your QC. What is your QC? Your QC is, this is the one. Okay, let's just substitute into here. And plus with your QP is 3 over 38. And now we have our general solutions for this RLC circuits. But remember just now we have the initial conditions. Okay, so we have these two initial conditions that we have not used yet. Okay, so we need to use them. Okay, so we're going to use these initial conditions, continue to solve. Okay, So we have the general solution Q. Let's just name this equation as equation number 2. Okay, now before we do the substitutions, okay, let's just look at what we have in the initial conditions. You have I0 equal to 0 and you have Q0 equal to 0. Where Q0 equal to 0, you can use it in equation number 2. But for the I0 equal to 0, you need to have the equation I. Okay, so you can obtain the equation I from the I equal to dq dt. Okay, so which means that you need to differentiate your equation number 2. So if you differentiate your equation number 2, basically you need to use the product rule here. So means that you have to let your u equals to e to the power of negative 5t, and this is actually your v. So your I will be equals to u dv. Okay, your u is e to the power of negative 5t multiply with your dv plus with v du. This is your v. Multiply with your du. So your du is negative 5t to the power of negative 5t. Okay, and we name this equation as equation number 3. Let me erase this one. Alright, okay. And the next thing that we have to do is you need to do the substitution. Let's substitute this one first. So we're going to substitute Q0 equal to 0 into equation number 2. So means that your Q is actually 0 here. And your time is actually 0. So we have e to the power of 0 in here. And you will have, this is 0. So 25 3 multiplied with 0 will give you a 0. Then you have sine 0. Sine 0 is 0. So you have a multiplied with 0. And in here you will have cos 0. So cos 0 is 1. So you have b multiplied with 1. And you have 3 over 28. Okay, then simplify it, we're going to get the value of b. Okay. Then we have I0 equal to 0. So substitute this one into your equation number 3. So your I is actually 0. Your time is 0. So you have e to the power of 0. And this is cos 0. Cos 0 is 1. So 1 multiplied with this. And you have sine 0. Sine 0 is 0. 0 multiplied with this. And you have here, this is 0. So you have sine 0 is 0. So 0 multiplied with a. And this is cos 0. Cos 0 is 1. 1 multiplied with b. And we have e to the power of 0 in here. Okay, let's just simplify it. Okay, so you simplify. Okay, this is 1. And this is 0. So we have this one for this term. Okay, for here, this is 0. This is b. And we have negative 5 here. So we have negative 5b. Okay, b is actually negative 3 over 38. And then we simplify it. And we're going to get your value of a, that is the 1. And substitute your value of a into here. And substitute your value of b into here. Then you obtain the particular solution. So this is the particular solution for this RLC circuit.